All right, good morning. We have an absolutely beautiful Wednesday. 3 days left in this summer term. So we're really getting down to the end here. And, as I mentioned in yesterday's video, I design my courses, very purposefully. You'll notice that if you pick up any sort of particular macro textbook, that we've not followed any discernible order laid out in those books. In a sense, this is sort of the way that I like to lay the class out. And as such, the kind of big idea here at the very end is we want to kind of sort of push our economic thinking into that very long run. And it's not, to really suggest that we need to think either in the short to medium run, think in terms of economic fluctuations, or we need to think in terms of the very long run. Obviously, it probably goes without saying that we need to balance these two, and we certainly need to be thinking about them both at the same time. I think, one of the sort of interesting things about, where we find ourselves in terms of macroeconomic thought in 2025 is how much, in terms of the general population, politics really dominate this sort of conversation about macroeconomic policy. But to economists, we really arrived or got to a point in macroeconomic thinking, for the most part at least, with perhaps more consensus than there's ever been, and really not much left in terms of these sort of rigid schools of thought that sort of separated and kind of caused all these debates and everything. Not to say that those debates weren't good. I think that they were completely healthy for the most part and most times. But it is interesting, I think, that in the general population, we seem to be so very much more polarized on economics, and then economists are less polarized. And that's, both good and bad, of course. It's great that economists are sort of in much more agreement than we used to be. I think that over time maybe can spill over and give people a little bit more clarity in terms of sort of what we should be doing and maybe what we are doing. But I think, the nature of economics and I can only speak to the U.S. experience, but I'm sure it's true in most other places as well. The distorting and the warping of economics to suit political goals, to purely political goals. And there is a world where politics and economics coincide, and sort of maximizing the economic outcomes of your country would be rewarded with electoral victory. That doesn't always work, and part of the issue is that people don't necessarily fully understand the history of these particular things. In this class, we spent a long time, kind of perhaps at times, maybe annoyingly so, on the sort of historical context of these theoretical breakthroughs in economics to really kind of understand, where did these questions originate from? Why did we go about trying to answer them in the way that we did, perhaps differently than the way they had been attempted to be answered in the past? And then sort of after all of that, where do we kind of find ourselves? And so my hope is that we're going to sort of end the semester on probably the least politically distorting way to think about economics, which is just growth. Economic fluctuations, fiscal monetary policy over the short to medium run, a lot of debate, a lot of consternation, and you can get caught into traps, not just liquidity traps. That's a dad economics joke. But with growth, there's obviously some philosophical arguments against economic growth. There is a so-called degrowth movement. Most economists, really reject that particular concept. We find that economic growth is incredibly important. It isn't the end all be all in the short run, but over the long run, economic growth is incredibly important to the livelihoods of people in respective countries. If you look at, what is correlated positively with economic growth, education rates, infant mortality declines, basically everything that good that happens is positively correlated with economic growth. There, of course, are some negative things that have historically also been correlated with economic growth: environmental destruction, income inequality at times, labor market exploitation. That's so not to say that because those things occur, therefore economic growth should be abandoned. I think is very, very problematic. So regardless, let's kind of end that little preamble into this, and then let's kind of talk a little bit more about this idea of golden rule. I'll take you through a numerical example of golden rule, and then we'll give a little bit of commentary. And then in the next video, what we're going to do is we're going to introduce a new angle to the Solow model and try to sort of talk about the effect of productivity gains, specifically labor productivity. Okay, so in the golden rule, what we need is two conditions, essentially, right? You'll notice that throughout the semester, I've always framed a lot of these questions in terms of conditions. Like, we need this to be true, and we need this to be true. And if both things are true at the same time, then we've achieved some notion of optimality. That's a very common thing in economics, obviously math as well, and physics. So here, the golden rule says that two things are true. One, the economy is in steady state, so it has achieved a steady state position. That means it's no longer accumulating capital. It's no longer shedding capital. Year over year, the capital stock per worker is unchanged. Now, that gets somewhat complicated when we start, thinking more directly about population growth. Right now, we've sort of hand-waved population growth away. We'll talk about that in just a moment, because it certainly complicates the concept of golden rule, and again, in ways that are at least somewhat counterintuitive. Okay, so we need the economy to be in steady state, and then the second thing is that we want to maximize consumption. Now, that second point, maximization of consumption, we're going to pull from that economic theory that we developed earlier in the semester to come up with a fairly simple rule here, which is that consumption is going to be maximized when the slope of the production function with respect to capital per worker, so that's marginal product per capital per worker, when that is equal to the slope of the depreciation and population growth line, which is just delta plus n. Now, again, I think very often when you're learning this stuff, you just want to kind of learn the rules and sort of work through things. But it's important to sort of recognize the economic logic here, the economic reasoning of what's going on, and to really kind of think about this in terms of that sort of on the margin thinking in economics. So this says literally that the extent to which you increase production by adding capital per worker, so that's MPK, that will maximize consumption when that rate is essentially equal to the rate that we are using capital in our economic system, where we think about using capital again as to what extent are we losing capital through depreciation, and then to what extent is capital being used, by units of labor. Okay, so just to sort of keep that kind of theoretic concept in mind. So now let's work through a relatively simple numerical example of how to find the golden rule steady state. So again, we need these two conditions to be true, and so the first step we're going to do is we're going to set up, in a sense, the condition within the consumption function, right? So we're going to start from the perspective that consumption, C, is equal to output, Y, minus investment, I, right? And then, so we can just expand this out by plugging in, oh, by the way, I don't think I mentioned this, but we're going to keep that same production function that we've been discussing the whole time. So I probably need to have a production function there. So our production function is going to be square root of K, which is our common production function. Okay, and so again, we're just going to expand out our apologize for that. I was hearing a weird noise in the background and it kept distracting me. So I've got that figured out. Now we can come back to this. Anyway, so we're going to set up the consumption function. And then what we're going to do is we're going to actually embed the steady state condition ultimately into the consumption function. But before we do that, let's just expand out the consumption function, as we said. So again, we know what our production function is. So K to the 0.5. And then again, typically investment is just S to, the production function. So SK to the 0.5. Now, the trick here is to remember that in steady state, investment is equal to depreciation plus population growth times capital. So what we can do is we can, recalling that in steady state, that S of Y is going to be equal to that, right? That's a steady state condition. So we just take our consumption function, K to 0.5, and then minus delta plus N to the K. And then we'll go ahead and put a star here. Ultimately, we're solving for a steady state capital. And in particular here, we're solving for the golden rule level of steady state capital. So now what we want to do is we want to differentiate our consumption function, right? Because remember, we want to have a level of capital and therefore a level of savings that maximizes consumption. So once we've differentiated consumption, we're going to set that equal to 0. So first, find C prime, where C prime is just the derivative of C with respect to K. So we go through, we take our derivative, 0.5, and then we'll go ahead and put this in the denominator. So yeah, that would normally be K to the negative 0.5. We'll go ahead and put that in the denominator as such. And then if we just go ahead and distribute our K through and then take the derivative, we just get minus delta minus N, okay? And again, we're going to take that and take C prime. We're going to set that equal to 0, and then we're going to solve for K. So let us do that. So 0.5 over K to 0.5. And then we're just going to say equals. We're going to go ahead, because we will have set this equal to 0 up here, right? And so we'll just go ahead and move delta plus N over here. Oops, sorry. You can go ahead and plug in the values for delta and N here if you wanted to. I tend to kind of like to do it at the very, very end, but you certainly could go ahead and plug it in here. It kind of depends on what you prefer. Okay, so we're just going to end up solving for K. So we'll flip the everything. So we'll put this 0.5 over 0.5 is equal to 1 over delta plus N. 0.5 there. Then we're just going to multiply both sides by 1/2. So K 0.5 is equal to 1 over 2 times 1 over plus N. And then we're just going to, we can, at this point, I think I would probably go ahead and do our plugging in of the values, just so ultimately when we square both sides to get rid when we square both sides to get rid of the square root, it'll probably just make our lives a little bit easier. So let's just do that. So we have 1/2 times, and then 1 over delta was, let's see, what was delta again? 10, and population growth equal to 10. So 0.20 there. We can just do the math. 1/2 times 1 over 0.20 is going to be 5. And then obviously that's going to be 2.5. So K 0.5. And then we'll just square both sides, obviously, to get rid of the square here. So what we're left with is K. And then this is golden rule. So not only a steady state, but also a golden rule is equal to 2.5 squared. And so 2.5 squared is going to, that one's not quite as easy for me to do. And we can see that, therefore, golden rule steady state capital will be 6.25 units of capital. So now we've established what the golden rule steady state capital is, but we still have to figure out what the savings rate we need is to achieve this particular level. But that's quite easy. So I need to find S that causes K equals 6.25. Okay. So we know that in steady state, right? So in steady state, we have that investment is equal to depreciation plus population growth capital, right? We now know what the golden rule capital is. So all we have to do is just plug that in and then solve for S. So we have S is equal to, this is going to be 6.25 is equal to in, let's see, times 6.25. S is going to be equal to 0.20 times 6.25 over, and then we'll just divide this over. It's just 6.25 raised to 0.5 there. And then we're just going to do a little bit of simple. Okay. So 20% of 6.25 is 1.25. And then the square root of 6.25 is, as we know, 2.5. And so we need a savings rate of 50%. A savings rate of 50% is going to give us K is equal to 6.25 when delta plus population growth is equal to 0.2. Right. So that's how we find golden rule capital here. So the idea is that wherever the savings rate is in the economy, policymakers want to move. So let's label this GR. Policymakers want to move that to 50%. If they move it to 50%, wherever the steady state is now is going to shift to a steady state of 6.25. And then, of course, if anything changes, depreciation or population growth changes, that, of course, is going to alter what the golden rule happens to be. So, this is the idea that we, in terms of golden rule. Now, again, the sort of big thing that we're interested in is what is the transition from the current steady state that hypothesizing that we're in steady state to the golden rule, right? I mean, because think about it, that's policy, right? That's the effect of policy. The policy here is we're going to target a particular savings rate, and then we're curious about the effect of that particular policy on, again, the behavior of output, the behavior of consumption, and all that. Now, the one thing we know about this is that if we're not in golden rule and we move to golden rule, we know that consumption is going to go up. In other words, if we successfully get to golden rule capital accumulation, then wherever we were to now, consumption is going to rise. The behavior of output, the behavior of investment, that is determined by where you are in the context of the golden rule. And so we can think about this, kind of in just the mathematical sense. And of course, what's always helpful here is the relatively straightforward Solow graph. And so again, the idea here, let's just go ahead and put a line there. I find this difficult to get the line right if you don't go ahead and draw it. So y, s of y, n plus delta k, right there, right? So the argument here is that, okay, currently we're here, k star. So we're in steady state, and but we want to move to golden rule steady state, wherever that happens to be. Golden rule steady state is going to be where the slope of the production function is equal to the slope of the depreciation population growth line, right? And so, for example, let's say that we're currently below golden rule. Okay, so let's just, again, hypothesize that golden rule steady state is going to be somewhere like right here. Call this golden. Okay. Then what's going to happen, of course, is that in order to achieve this, we have to increase the savings rate. Okay. So now, let's say we increase the savings rate. Oops. Let's not draw a completely terrible line. Okay, so now savings rate's higher. All right, now investment's higher. Now nothing else has changed, right? But what has happened, of course, is that output has changed. And we'll go here now. Output is up here. Y prime. The difference between output and investment is C. So C prime, and then the difference between C and Y is investment. Right. So you can, and so there's like the where they were, then where they happen to be, but then there's also the path that they take when they get there. And so this is where, we sort of try to shoehorn in the idea of this path concept into the simple model. It would be better if instead we used a multiple period model. I'll show you that model. It's a little bit more complicated mathematically, but it allows us to do a little bit more of these sort of transition ideas. And you'll see this, of course, come up in your problem set. But just for example, let's take investment. So we know that investment starts here. We can call that point A. And then we know that investment is eventually, oops, I got this consumption on there. Okay. And so you can see, how this gets really messy, right? Because the way that I've drawn it clearly looks like consumption has actually declined here as opposed, so you have to draw if you want to sort of show the movement to golden rule, you have to make sure that you draw the graph in such a way that actually achieves that. And so that's really the complication here. You can't sort of just haphazardly do it as you just saw me, because it doesn't sort of readily make sense, right? And so going back, let's take all this away and let's look at this idea here. So if we just look at this from the perspective of where we are in the context of the graph and relative to consumption and investment and everything, we can sort of, again, we know that this vertical distance here from output to investment, that this is the consumption, right? And so we can see, for a given level of change in investment, what's going to happen to consumption. So we have to ask ourselves, do we think consumption is going to increase if savings increases here? Again, graphically, we're just thinking about the graphically. There are no numbers here at all. Or do we think it looks more likely that consumption would increase if we decreased our savings rate, right? And so again, you can just sort of look at this. So this would be investment. This would be consumption. So you can see moving from here to here, we actually see that consumption rise. And so that's graphically, you have to be careful. You have to be careful you don't sort of work yourself into a corner there where you're not able to actually explain the paths. So now shifting over here to the slides, this is why it becomes a little bit easier for us to think about these in terms of these actual dynamic paths. And in your problem set, you're going to do an Excel example where you're going to set everything up in Excel, and then it becomes a really sort of simple way to produce these dynamic paths. And I will show you how to do this in Excel as well. Obviously, a different example than the one you have on your problem set, but I'll give you a lot of direction into actually how to set up the Excel sheet, but then you can just, basically simulate an economy, and then you can see the economy, if something changes in the system and the economy has to recalibrate to a new steady state, or in the case of in search of the golden rule, if policymakers push the economy to that golden rule, what does that mean for the various paths of output, investment, and all this various stuff. Okay, so the last thing I want to say real quick about just the basic solo model with population. Again, typically the way that you sort of teach this is you teach it with just the depreciation, then you tell students, okay, now we're going to add in population growth. I like to just go ahead and stick population growth in there, and then sort of later on explain, what that is. So as I've said to you before, you can think about population in a similar way that you can think about depreciation, because very often students are confused as to why population and depreciation would both show up, kind of in the same place, because you tend to think about population as increasing the output. So in this sense, why does it lumped in with depreciation? This is where you have to think differently about output, because here we're not talking about output, right? We're talking about output per worker. We're not talking about capital. We're talking about capital per worker. And so if population goes up and your capital stock stays exactly the same. Now, the idea here is that if your population goes up, then your labor force goes up. So if your labor force goes up, you have greater L. And if your capital stock stays exactly the same, now you have less capital per worker, right? So just mathematically, capital per worker declines. And that's the same thing, of course, if you think about this in terms of depreciation. What happens if depreciation rises? Capital per worker declines. And so you can't think it in terms of just like labor being added to a capital and labor production function. It's labor being added to a per worker production function. And so, but what this brings up is this really important economic concept called break-even investment. So the idea of break-even investment is that if you take your depreciation rate and your population growth rate, that multiplied by whatever your capital stock is now is the break-even investment, the investment that would leave your capital stock completely unchanged from one period to the next. And then obviously, if what you actually invest in is greater than or less than that, it's going to give you an actual change in the production function. Why this is so important is that if you tie this back to this idea that the economy is sort of moving forward with a combination of planned expenditure, actual expenditure. In this case, we can think about it in terms of the economy is moving forward with planned investment and then actual investment. And then the idea here is that planned investment is always going to be at least, right, in good economic times, at least break even. Right, we don't expect capital stocks to necessarily decline. The only reason why we would expect that is if you were actually above your steady state. But then keep in mind, we don't expect that to happen very often. We think economies are sort of constantly moving towards their steady states. Otherwise, there would be a bunch of countries who don't grow. That happens. There are some countries who aren't growing, and maybe they are too far past their steady states. Maybe they have over invested in capital stock and therefore just have a bunch of unused capital sitting around their country. That actually happens a little bit in the context of especially foreign direct investment. Very often developing countries will invite foreign direct investment. That flow of financial capital into the country will also generate a uptick in the amount of physical capital that's being generated in the economy, and then there can be a bunch of stuff left idle, not being used. And in that sense, the country has incurred the cost, the investment of the materials, but isn't economically benefiting from them. And so in that sense, it makes sense why a country beyond their steady state would actually suffer economic decline. So if we experience population growth, the model predicts that steady state capital will decline, and kind of all else equal, we're going to move to ultimately, therefore, a lower level of output. But output per worker, right? It's not so much that the economy has gotten smaller necessarily. It just means that there are more people, and if everything else stays the same, then there's going to be less stuff, sort of go around from an output perspective. So what does this mean? This says that countries with higher population growth rates will have lower levels of capital per worker. I mentioned to you before that very important sort of result, which is that the marginal product of capital ends up equaling the slope of the depreciation line. If we move depreciation over, in other words, we solve that condition for population growth, we get a very interesting result here, which is that population growth is going to be equal to the marginal product of capital minus the depreciation rate. So basically, thinking about that is the marginal product of capital net of depreciation is going to equal the population growth rate in the context of a capital per worker and output per worker system. What is the evidence of this? Pretty strong evidence that this is at least a weak relationship, but we can also look at some alternatives here. So basically, this argues that population growth is sort of it's good for an economic system because you can produce more. But the problem of population growth is that in terms of a per unit, a per worker consideration, there's this trade-off, to some extent. So like a lot of things, the idea here is that there is sort of too little and then too much population growth. And part of the too much population growth is that it reduces your capital per worker, which ultimately reduces your steady state level of capital. And so depending upon where you are economically, that might actually lead to economic dysfunction, leading to particularly recession, or at the very least, slow growth considerations, right? Think about economies that are far below their steady states. We predict those to be growing very rapidly. Think about economies that are far beyond their steady states. We expect them to actually be sort of contracting. And so you can imagine that if over time, very rapidly, there's this sort of extreme level of population growth, right? I mean, again, don't just sort of guess, right? Yeah, I'm always telling my son, don't guess. He's 4, but I don't guess things, right? Don't try to guess a word, sound it out. Don't try to guess a math problem. Work it out in your head or use your fingers. So we can do that here. That's the beauty of economics. So, okay, we have a current situation, output, investment, and then depreciation plus population growth. Okay, so now imagine that an economy kind of settles, or at the very least has a steady state here. But then over a couple generations, let's say there's very, very rapid population growth. And the rest of the economy does not readily change very much. The country doesn't become more productive. By the way, that's going to be kind of part of the sort of argument long term, is that if we have a production function that looks like this, y is equal to a k 0.5. This A we refer to as autonomous technology or autonomous productivity. The idea is going to be from a sort of development perspective is that if you can take advantage of population growth, basically if you can educate that population, if you can give them skills, if you can make that population productive, then you might increase A. And if you increase A, that's actually going to lead to a higher production function writ large, right? Right. So that's possible. The concern is that in a country perhaps that doesn't have good systems, good healthcare systems, good educational systems, they're not going to be able to bear the weight of that extreme population growth. So the population growth, in a sense, is going to happen way before the production side sort of catches up. And so if you just sort of do this and you say, okay, delta plus n prime times k, where n prime is greater than n, right? So population growth has increased. Then again, you can see that the result of this is that we have a pretty substantial decline in steady state capital, right? And then if you look at what this then means ultimately for output, right? Boom, right? So the idea here is that sudden population growth that is not coupled with any sort of improvement in autonomous productivity is ultimately going to cause economic contraction. So the trick of long run economic growth is basically to prepare yourself for population growth by also adding to your autonomous production, such that if you do experience this population growth, you will also experience productivity growth, say something like that. And with that level of productivity growth, you're also, of course, going to shift up the savings, the investment in the economy to something like that. And so you might, in fact, be able to reverse back this idea. So that's the trick of economics, is that in growing economies, we tend to expect population growth to sort of pick up speed, right? So once you kind of have decent healthcare systems, just a little bit of economic growth goes a long way in terms of population. You don't need a good economy to have high population growth, but you need just a little bit of economic behavior, and then you sort of get this like big population growth spurt in some places. The thing about that is that the population growth spurt is also tends to be negatively correlated with things like educational rates. So countries that have higher education rates also typically have lower population growth rates. So education becomes one of those sort of moderating things to kind of keep that population from sort of really spiking in that particular direction. And then, of course, education also feeds its way back into increasing the actual, sort of production function, as it were. And so when we look at kind of what causes economies to kind of grow over the long run, it really starts to feed into this narrative and into this story that it's about two key things. It's about productivity. So it's like, how productive is your economic system? That obviously has a lot to do with technology, especially in 2025. But then the second component of that becomes a little bit, I think, optimistic and not so much about economics, but more just about sort of the fundamentals of society, is quality of institutions. So we're going to move into the endogenous growth model tomorrow, and that basically argues that the key to economic growth is institutional quality, legal system, property rights systems, political systems. And ultimately, the Solow model informs this particular idea, because in the Solow model, if you're going to have population growth, that needs to be coupled with productivity growth. Otherwise, your economy is just going to continue moving backwards. In the US, what we have done very, very effectively, and I'm not necessarily saying this is just about policy, is that we have been able to couple, even at times, fairly significant population growth with even more significant technological growth, which in a sense has allowed our economy to absorb that population growth. And so in that sense, you sort of go back to that classic like Malthusian argument, right? Malthus was this classical economist. We don't often lump him in as much, unfortunately, but his argument was runaway population growth was going to be the doom of economic systems. And so, his argument is that population grew, geometrically. Let me bring here. So his idea is that the population growth, so over time, so population growth grew like this, and productivity, or what he sort of referred to as productivity, which was mostly about the ability to grow food, productivity was linear. And so at a certain point in time, we'll call that T dot, you would start to have sort of large scale unsustainability, right? You could have sort of full kind of societal collapse. This happens. So like, this has happened at times throughout history. It has never happened on a very large scale to the extent that Malthus sort of predicted it to happen. But from a development perspective, one of the real sort of puzzles of how to grow an economy that has not historically grown very quickly but has experienced very rapid economic growth, it basically ends up becoming a story not so much of, how do we take advantage of this population growth, but we have to grow the economy to accommodate the population growth. Otherwise, we're going to push it towards the brink potentially in some position of this. One of the nice things is that in 2025, we've actually improved a lot of these sort of unsustainable economic positions that a lot of countries found themselves in the especially the 90s. The sort of entire continent of Africa was really in many ways kind of on the brink because it had these very rapid bouts of population growth, but then economically it was still suffering from decades and millennia of things like colonialism, but then just bad sort of economics, bad legal systems, bad property rights systems, bad economic and political systems, which didn't take advantage of the population growth, and then as a result, of course, became a fairly miserable economic experience for a lot of people in question. If we look at kind of the modern day Middle East, we start to have concerns there as well because you have high population growth, but you have very kind of middling economies. That's not every economy in the Middle East. Luckily for the Middle East, they have a lot of oil that helps their economies kind of buoy that sort of production conversation. But again, we're sort of moving back into this idea of crisis, right? When we talk about Keynesian ideas, that was sort of the crisis of economic fluctuations. Now we're kind of sort of confronted with the crisis of needing to ensure that we have consistent economic growth over the long run, because getting this wrong is very troubling to indeed. So we say here Malthus neglected the effects of technological progress. I mean, that's probably unfair. I mean, Malthus is writing in the late 1700s. What technology could he have necessarily foresawn? But I also think that the sort of over optimism of technological progress, given the fact that we live in 2025, we've never had the extent of technological diffusion that we have today, right? Technological diffusion is just the spread of technological knowledge across the world. It's never been faster today, and yet we still have it the case that rich countries have much higher access to technology than poor countries, and that ends up being a big thing that holds back poor countries. And so, one of the things really that could facilitate the idea of economic development, I think, is a much more harmonious and sort of partnership model of rich countries and poor countries, mainly on the basis of technology diffusion. And then also, I think we can kind of go back to the system of really helping these countries with their economic policies, because the solo model kind of gets us to a point, which is that, countries like the US, sort of developed economic systems, they don't really have these necessarily sort of growth issues. We've sort of figured out or unlocked the growth puzzle, as it were, in the US. Stability, low inflation, relatively low unemployment, consistent, not too high, not too low economic growth. In developing countries, you have much more fluctuating real business cycles. You have poorer policy in the context of the goals and sort of perverse incentives. And then, of course, you have things like corruption, and that also, which tends to decrease the efficacy of economic policy, and therefore also reduces the economic prospects going forward.